So finally, we have Eric Posma, who is a manager of our Maplesoft Math group. He will show us how to create and use structured types in Maple to improve our Maple code. So please go ahead, Eric.
Thank you. Let me share my screen. All right, I'll do my whole screen. There we go. Okay, I have a worksheet here that probably almost certainly contains more content than we have time for, but I'll make sure to select the bits that I think are most relevant to the most people. So we'll talk about types in Maple and structured types in particular, and what you can do with types. And I want to start with one command that, how do I say this politely, that I'm not a huge fan of, but it's useful because it gives us something to talk about, an important point about types in Maple. So this is the what type command, and we see many users use this. It's certainly a useful way to get a first impression of what a particular big expression that you don't know anything about is. It's very simple. You give it an argument and it gives you a type that argument has. So 7 is of type integer and 3 plus 2x is of type plus. Now, you might have noticed there that I formulated very carefully. I said it gives you a type that expression has. If you're familiar with programming in languages like Python or C++ or basically almost any other language, a type is, there's only one type basically that every expression has. That is its type. And from that point of view, the command what type would be very useful. But in Maple, there are many different types that apply to every expression. So these examples, we can be more precise than that if we want, and we can use the type command to do that. So 7 is not only an integer, but it is a positive integer, and we have a type for that. It's called posint, or we could describe it as a non-negative integer. And so the type command takes an argument and a type, and it will tell you whether the argument is of that type. So, for example, 0 is not of type posint, so we get the result false here. But it is of type non-neg-int, right? It is a non-negative integer. And there are many types that are built into Maple. Just zoom in a bit here. We can see that some of them are listed here on this help page, and it starts here, and it just keeps on going. Okay, so this is not something that you should aim to, try and remember all of the types. That's just a reference for what we have. Now, more importantly, there are also types that take parameters, and many of those are listed here on this help page. Again, I'll zoom in. And we call them structured types. And this is a very dense help page. I open this probably once a month to look something up, even though, I've been programming in Maple for 17 years, and it's not really all that much in volume, but there's a lot of depth here in this page. So we'll see a little bit of these detailed, structured, parameterized types. I'll give you one example of a type that has a bit more of this detail. So we have 3 expressions here: 2 plus x squared, 2 plus sine of x, and 2 plus y squared. And if we ask which of these expressions are of type polynom, then it will tell you that the first and third are of type polynom, but we can be more precise than that. We can ask which of these expressions are polynomials in x with rational coefficients. And in that case, Maple will tell us that this one is not, right? Okay. Okay, let's move on to what we actually want to do with these types. I would say probably the most important application of types is parameter processing. So this is what makes your code more reliable and easier to use. So let's look at an example. You define a procedure, add to all, where you pass in a list and a value, and what you return is just you add that value to every entry of the list. Okay, that's great. And now, 5 minutes later, you want to use your procedure, and you say, okay, add to all. I pass in my value, and I have that list. And what you get is something weird. You just get this value 3 plus the list 579. It turns out that what you did is you forgot that you wanted L to be the list and X to be the value, and you passed them in the wrong order. And because we haven't told Maple that we specifically wanted L to be a list and X to be a value, it doesn't complain. It just does what you tell it to do. But it makes it a lot friendlier for your users, which includes yourself, if you add these type annotations. So if you have a procedure and you list the arguments, then you can use a double colon and then specify a type. And so here's an example. The type algebraic is very useful to know. That's basically anything that you might want to add or multiply by. In the sense of scalar values, let's say. If we have a list of, let's say, scalar values and a value, then so this is our new definition. It's the same as the old one, but we have types added here, and I won't go into detail in this talk about the end of parameters marker. They talk about that so often that, but I would highly recommend adding that to the end of just about all of your procedures. All right, so now if we do the same thing as before, we get, instead of this unexpected result, we get a useful error message. Add to all, expect its first argument L to be a type list of algebraic. Okay, so now we know, we need to switch that around, and we get the argument we expected, or the result we expected. Okay, the next step in this is if we have multiple procedures that accept different types, and we want to make one sort of front end. So we could define a similar thing for strings, where we have a list of things that could be either a string or a symbol. Everybody know what a symbol is? Probably not. A symbol is basically a variable name in Maple. So if you say type Z, symbol, Maple will return true. And many things in Maple that deal with strings can also deal with symbols. So it makes sense to accept both. And since we are talking about structure types, this is one of the most useful, most basic structure types. If you specify a set of types, that is a new structured type that includes all of the values that are of any of the types in that set. So this type that I've highlighted here includes strings and symbols. And we have a list of such values, and then we have a string or a symbol that we want to append to all of these. Okay, so how would we use this? Well, we have a list of Maple versions, or Maplesoft products, I should say, and once we release the .2 version, we add .2 to all of these strings. All right, great. Now, if we want to create one front end for both of these, for sort of both of these types of functionality, which might be reasonable, then what we can do is, so like what Matt showed, I really like if we have a bunch of related procedures. I really like wrapping them up in a single module and adding a module apply method. And so I've done that here. We often do that with this thing called an overload. So how this works is we give this overload a list of procedures. This function called overload, we give it a list of procedures, which we can either define right in line like this one or beforehand. And what it returns is a new procedure that tries to apply each of these in turn, and provided that we give them this option called overload call seek only, it'll try to match the argument sequence to the parameter sequence, and if that works, it runs this procedure, and if it doesn't work, it goes on to the next one. So that was a whole mouthful, but if we actually run this, then you'll see that it makes sense. This is basically what happens here is we call this overload procedure with this argument sequence, which is a list of algebraics and an algebraic. So it tries to call add to all strings, that fails. It tries to call add to all algebraics, that succeeds, and then it returns that result. We can do the same here with a list, in this case, of symbols and a symbol, and then it works the first time and we get the result there. One issue is that the error message gets a little bit worse in this case. We do get an error message provided that we put a procedure here at the end that generates a good error message. But we need to do a little bit of work to make sure that this is as easy to understand as what we saw beforehand. All right, I don't have much time left, so I think probably the best thing out of these three is this subs-index procedure. I just want to show the first entry here. What subs-index is extremely useful for is if you have a complicated expression and you want to do some sort of pattern matching for sub-expressions, and you want to make a particular change or apply a particular operation or just record some property of all sub-expressions that follow a particular pattern, then what you want to do is find a type that describes that pattern and then call subs-index. Here we have a very simple case study. We have this expression. Now, if we evaluate it, I put it into unevaluation quotes to be able to operate on it before evaluation. If we evaluate it, we see we get 0.99999. So what we get here is a round off error, right? If we want to deal with this expression in any way before evaluation happens, we need to tell it to do only one level of evaluation, like we do here. And if we call simplify on this, we still get that round off. But here is the call to subs-index that I wanted to show you. So we take this expression, we do only one level of evaluation. So that gives us, rather than the name expr, it will give us the expression that you see here. And now we specify a type, in this case, the type float. And what subs-index does is it will walk the whole expression tree for this expression. And whenever it encounters a float, it will apply this command to it with an extra option that we can specify here. So basically, it will turn every float that it finds into a rational. So instead of 3.14, that will be 157/50. And now, of course, if we simplify this, we get an exact result.